So, unfortunately, our original moderator could not show up today, so I will be your bad variational local optimal approximation to him. I'm Trevor, a postdoc at CCEL and at MIT. We have an excellent panel of speakers about software and approximate Bayesian inference for you today. Just setting up right now are Mike Hughes on the far end. He's a postdoc at Harvard. We have Daniel Ritchie beside him, who is a postdoc in CS at Stanford and soon to be an assistant professor at Brown University. We have Ryan Sapasi, who I believe is a software engineer at Google. Dustin Tran, who is a PhD candidate at CS in CS at Columbia. And then on the very far right, we have Aki Vatari, who's an associate prof at Aalto University. So let's kick off the software panel with just some brief introductions of your history in approximate inference coding, maybe why you got started, what motivated you, and some recent projects that you've done. Why don't we start with Aki, who has the microphone. And by the way, we only have, unfortunately, this one microphone. So the crowd, unfortunately, if you want to ask a question, maybe just raise your hand, I'll point you out, and just yell at the panel.
Is this on? So I started the 1990s with neural networks and first with non-Bayesian. But also then soon to Bayesian inference, first MCMC, Blackbox, then I moved to Gaussian processes, and then again MCMC, expectation propagation, Laplace approximation, importance sampling, recently also likelihood-free inference, ABC. They have a poster about the engine for likelihood-free inference next to the door. And then I'm also part of the STAN development group, and then helping there with the, especially about the model assessment, estimating model predicted performance, and there again these approximate models there, helping with GPs and we've got in several, been in the development of several different software, GP stuff, STAN, FP, so.
So as many other grad students, I've mostly been putting up stuff as a way to get interesting experiments, to explore stuff. And really what I've been doing, I really started in learning about Bayesian statistics, trying out a few things, starting at Harvard, working with people like Don Rubin. And I really got interested in STAN because it was one of the more interesting ways to sort of posit flexible models for the structure and do efficient inference. And more recently, I've been working on this software library called Edward, which is trying to more closely bridge the gap between some of the more interesting deep learning methods and frameworks for proximate modeling.
So I came to Bayesian inference through the software world, specifically Tensorflow, and a group at Google called Bayesflow, just trying to introduce some of these methods into Tensorflow. And I guess we really started in deep learning land, and so we were particularly interested in these inference network variational approaches, and so that was the direction we've headed in, and that's the work I've been doing over the past kind of 6 to 12 months, yeah, so less of a storied history than these in these parts.
Yeah, so I have a bit of a different history, maybe an unusual one. I actually come from a computer graphics background, and my interest in inference started with trying to find ways to place conditions and constraints on really complicated generative processes that generate visual content, like images and 3D models and things like that. And there were really no good existing software packages for doing this kind of thing. Everyone was kind of rolling their own code, and so I got interested in sort of universal probabilistic programs, things that kind of allowed you to perform inference on any sort of computable process as a possible avenue for making it more generalizable. And so I kind of started off doing a lot of Monte Carlo stuff, MCMC, sequential Monte Carlo, and more recently I've been looking a lot at variational inference, unsurprisingly, and amortized inference methods along those lines.
Thanks. Yeah, so I guess I started my grad student career as sort of a classic large-scale Monte Carlo MCMC style inference for these Bayesian non-parametric time series models. And I just quickly realized that downloading other researchers' MATLAB code and trying to run it was kind of a real pain in the neck. So I really got interested in building my own toolbox that, you know, tried to do things really well. And then I quickly discovered that variational methods were quite exciting. And so that's how I built kind of the later part of my PhD, is doing sort of Bayesian non-parametrics in Python at large scale. So that's kind of where I'm coming from. And, you know, I'm excited about all these new techniques, autoencoders, etc. at the workshop here.
Cool. So now that we know who our speakers are, why don't we open it up to the floor? Any questions that anyone wants to ask, go for it. Just maybe put up your hand so not everyone's screaming at me at the same time. Now, before we go on, can everyone in the back hear that, or do you want me to repeat questions? Okay. Yeah, actually, you know what? Why doesn't the speaker summarize the question before they answer? That might be easier to do instead of all this back and forth.
The question was, what are the sort of numerical tips and tricks that we've been using in developing sort of code bases and running the experiments that we typically do? My personal experience, and especially with Edward, has been that we've been trying to leverage deep probabilistic or deep generative models, and there are a lot of tricks. It really depends a lot if you're going to do, for example, if you're going to do unconstrained sort of transformations in order to optimize particular parameters that live on the positive space, for example. And the common approach to doing this is to do like a log transformation or an X transformation in order to go from positive to real space. What I found is more useful is like a soft plus, which is sort of a middle ground that smooths out a ReLU activation function. And you can see just by taking gradients and looking at the boundary conditions of this, that this is a little more efficient, as one example.
So all the papers have equations showing densities, and then you have to really do it all in block densities, and that's what comes again and again. New students don't realize this, and people have problems with kind of the when you then take averages over densities, but you're working on the log scale, you have to remember the correct computation order.
Do we have any other questions? Sure.
So the question was balanced with very generic approaches, and then on the other end, conjugate approaches and more structured. And so Stan tries to be this really generic, but then of course the cost is that for some models it can be slow, and then you can make specific inference approach for those specific models to get them really fast. But when you have that kind of software, then it's not so easy anymore to modify or extend your model, because then you would need to again change also your inference model. So I would say that there's of course need for both. It's nice that you can sometimes really quickly make new models, extend them and so on, but then you sometimes also need a lot of speed, and then you need to do these model specific things.
What I really like about Max Talk is that it's a good example of this, in the sense that you're really trying to bridge this gap between leveraging a very specific model structure and also incorporating black box techniques as sort of a default in case you can't leverage that model structure. And I feel like a lot of time in project programming, I feel like this occurs all the time, especially when we're doing sort of automated or generic inference. There's sort of this promise that you can posit any probabilistic model and we can do efficient inference on this. But in practice, this isn't really the case. We typically posit our models based on what we know will do sort of efficient inference. And in building sort of these frameworks, I think it's sort of useful in order to help bridge this gap in some sense, that you can build maybe probabilistic programming languages that identify that model structure for leveraging that within an inference algorithm.
So as we move on to the next question. Go for it.
That's a good question. So in STAN,
Well, if you want to repeat the question first, just so that
sorry. So
poor
the
people in the
question
back
was
can
that
hear.
you have a model, an approximate inference, and then you get result you did not expect. How you find out whether the problem is with your model or with your inference. And now in STAN, there's also the order deep variational inference, and then the problem is really that it can fail. And then the problem is that how do you know whether it failed? Well, then you run Hamiltonian Monte Carlo NIPS to find out that. So, in a way, in those cases, you just need to use better inference methods to find out whether the problem is with the model. Of course, then if there would be a problem with the speed of MCMC, then you would just go to a smaller case of that specific model to try to find out that if your model is doing something sensible in small scale, and then if it works with these best inference methods, then you can go to approximately. If it still works, then you try to scale it up.
Yeah, so one of the things that is nice about, I think, working with probabilistic programs is that, in principle, if they're implemented well, that it's relatively easy to swap out different strategies for the same model without having to change it. So when you do get into these situations where you need to debug and figure out, what inference strategy is going to work best, that's relatively quick to do compared to if you're sort of rolling your own code and all of your inference code is mixed up with your model code, and it becomes much more tricky.
I guess the last thing I'd add to this is that I almost always figure that I have an inference problem, because on data that's big enough, you're really hardly ever going to be converging to something that's really the right, the best that the model can do. So almost always, you're running dozens or hundreds of initializations, and you're really trying to maximize what you can do with a particular algorithm. And if you're, that's sort of step one. And I think I'd echo what Aki said earlier, that really trying to use these general purpose tools that we have as baselines, just to see what's possible is really the right way to go.
I like to be a little devil's advocate here, and I think that using different inference algorithms is useful, and it's certainly a way of separating out these two different modules in some sense. But I think it burrows the problem into using the better inference algorithm if you could have done it in the first place. And in general, most of these inference algorithms are approximate. Even if you're trying to do MCMC, you're not sure if you're capturing all of the modes of the series distribution. And most of this is really a sort of open research challenge in the sense that we have ways of checking fitted models based on stereoperative checks, just looking at prediction accuracy if you're doing some supervised learning. But there's no good way of teasing out how can you really assess how your inference is really working. Something like convergence diagnostics for MCMC, but for approximate inference more generally. And how do you check, just from my model, how well is it going to capture the data hypothetically by the exact inference I want it to do?
I was going to say a similar thing that especially in the future it's more and more important we develop also diagnostic methods to find out whether it's an inference problem and then kind of how these diagnostics can help also then to identify what to do next.
Why don't we move on to the next question? In the back.
Yeah, so let's take complex, all right,
Sorry, it's quite a large room.
Okay, let's take a complex time series model, and I can run a particle filter, I can do pseudo-marginal and particle widths, and get what I believe is the correct answer. The question is, do we have, what are the challenges and variation inference in that complex time series here? I mean, we can scale it up as I mentioned, but what are the challenges in terms of variation methods sort of failing in complex time series models?
I guess I could answer that since I work a little bit on this. I think one of the main challenges that we've sort of been trying to advance in more recent years is to build more expressive approximating families, where if you're trying to do like posterior inference in a time series model, we often just assume that everything factorizes, that the posterior distribution does not depend on previous time steps. And this is really limiting, especially in the case of relational data or these sort of non-IAD data. And using some of the things that we've been doing in recent years with leveraging transformations to build expressive distributions or using auxiliary variables to possibly do diffusion processes or any of these other things can get slightly at that problem. And there's also the thing about commutation, namely that if you're doing sort of these first order gradient descent methods and you're leveraging more than one data point, it will typically not work. And the reason it typically does not work goes back to this problem that Matt was showing, which was that if you're trying to optimize this local variational factor, you really need that thing to converge and actually achieve the maximum in order to optimize any global factors. And Blackbox approaches are not really well suited for those sort of problems.
So I think this is, still a kind of open research area, but I think there was some good work presented, here at this conference on introducing stochastic layers into, big RNNs and doing kind of this general variational inference without, having the nice structure of, kind of real nice probabilistic graphical models. Also similarly, DeepMind had the draw paper. It's kind of a similar, approach, merging variational inference and these, big recurrent neural nets. But yeah, I mean, we still don't have a solution.
Just along the lines of what Dustin mentioned about being able to build sufficiently expressive variational approximations, I agree that's definitely an issue. And one of the things, so the language that I work on, Web People, our implementation of variational inference basically allows you to write your variational approximation as a general program. You can imagine it sort of running sort of side by side or in parallel with the forward generative model, which we've kind of just gotten started in exploring that direction. But I think that can be a very powerful way to kind of express arbitrarily structured variational approximations.
Next question. Sure.
So the question was about the software support for doing structured variational inference, specifically the availability of both good libraries for building large parametric models like neural networks, as well as software support for things like message passing. So Tensorflow right now does not, at least out of the box, have message passing algorithms kind of built in. Tensorflow is still, as big as it has become, it's still actually pretty new. And the Bayesflow group is even newer. So we've built up, a nice distributions library. We've added some facilities for variational inference and building kind of simple, kind of stochastic graphs. Message passing is not on the immediate agenda. We're playing kind of catch up on some of the more developed libraries, particularly, Stan is fantastic, has almost everything baked in, and so I think sampling methods are probably some of, on the more immediate roadmap, but I agree that is an issue right now, not having software support for both baked in, but hopefully that will change, and apologies that it's not already solved.
I'd like to add to that. So I've been working on this thing called Edward, and one of the motivations was precisely to solve this question in some sense, or at least to get closer to solving this question, which is to leverage efficient sort of model structure if you can. Otherwise, you do black box approaches. And I think there are really two main challenges. One is having the right foundation to represent all of these things, both in the probabilistic model and in representing very complex or very simple inference algorithms, and being able to compose these things sort of as you will. And Edward has been trying to get at this, and we sort of have this paper at iClear that I think solves that issue. The other one is really just implementing all these things in and doing these things well, namely leveraging all these sorts of tricks that people sweep under the rug. And Matt Hoffman especially has been working with us in order to get at sort of this conditional conjugacy structure. And once we implement that, then leveraging sort of the compositional representation that Edward provides, this makes it a lot easier to do the stuff that Matt Johnson was presenting.
So I'm gonna punctuate this sequence of questions with one that's sort of at a more philosophical level, and this is especially important for the students on the panel. What is good and bad about the current incentive structures for making good code during your research studies? And I suppose, how has that affected you personally during your work? Why don't we start with Mike?
Incentive structures, yeah. Luckily, I had a PhD advisor, Eric Sutter, that was very interested in sort of the very practical aspects of things, and he didn't mind if my weekly update was, oh hey, I was really hacking at this Python library, and I can basically do what I could do last week, but a little bit better. I think as a community, it's nice to promote development of packages, and I think it's really hard the thing that I found hard sometimes is that you can get the library to work for yourself, but doing that next level work of making it shareable to other people, I think is not often part of the incentive structure, right? You can write your own library, you can run it on your computer, and you can publish a paper off of that. But there's very little incentive to make it reproducible to somebody else. Often the journal review process doesn't require that, and I think that's the thing that we need to change.
Yeah, you pretty much just said everything I was going to say. Yeah, do I have anything to add to that? Yeah, I guess nowadays in sort of the social media era with GitHub and things like that, I think that there is a bit more social incentive to develop software that others can use. But yeah, there still isn't really kind of that top level incentive from things like conferences or journals to really push that effort to the next level. So I don't know what the solution is to that problem, but it's certainly something that could be looked at more.
Not sure this applies to me.
I certainly think that in order to solve this, the reviewing system needs to change. And we know that from lots of deep learning work or conferences or subfields, I guess, that they're a little more flexible in the sense that if the research is more engineering really than some advance in methodology, that this is still very interesting. That I have very cool experimental results, and I don't quite understand why it's working, that this is still worth publishing and still worth exploring and sharing among other colleagues. And we don't really have that in the PGM sort of community or in statistics. And I think we're slowly going to get to that. We're not quite there yet.
So there's a lot of these software packages which implement really cool methods and so on, but it's really a lot of work required then to make them to software tools to be used like STAN is used by many scientists in their own fields, and they realize that everything put in STAN really works, that they don't need to worry. And now the AABI was a little bit kind of problem that it was too hastily put there, and then people are surprised that, oh, it's not giving perfect results as they expect. The STAN is in a lucky situation that there are also coders who don't need to care about their academic career. So they can focus on that. But it's still, the to-do list is really long. There could be much more things put there if there would be more resources. And it's difficult in academic world. Funding institutions say that, oh, you are just implementing old idea. But it can be really valuable idea which would help, again, huge amount of scientists doing their own research. Now there are also, so in the neural network field, there is companies putting a lot of money, and it's there the packages are evolving in a more professional way. It would be nice also to get in probabilistic programming more funding, more resources.
Yeah, I think it is a good point that it's very difficult to get, I think, truly usable software when the only people working on it are grad students who have largely other concerns, like graduating. So I've been working on a DARPA grant for the last several years about probabilistic programming, and we've had a sort of a full-time software engineer on the project over the last couple of years, which has been totally invaluable. I mean, the language would not be anywhere near where it is today without the work that he does. His name's Paul Horsfall. He's based in the UK. He's incredible. I guess the point I was trying to make is that, so I think that some funding agencies are a little bit more open to that kind of idea. I think like DARPA in general and sort of DoD programs overall are a little bit more open-minded to funding kind of more just engineering work along those lines. But yeah, it's a tricky question. I think that maybe sort of it's kind of an if you build it, they will come sort of problem, that if we demonstrate that these kind of language ideas really can work and industry picks up on them, just as they have with deep learning, that there'll be kind of a natural just acceleration of progress in this area. So I guess maybe the answer is keep at it and convince the rest of the world.
And I just wanted to point out that Google is a software company. It's mostly software engineers, and while it may seem that the research is 100% deep learning, it's not. And there's more happening, and like Matt's work, and as more people join and are interested within the company in these probabilistic methods, there will be software support. And I think this is a huge benefit, not just of Google's open source effort, but of the open source effort across industry. And so as probabilistic methods become more popular and more widely used within not just kind of the company's products, but also specifically just the research org, even more research is being done in some of these areas in industry relative to the past, and hopefully that translates into kind of better supported software and better built out software. And the incentives for software engineers within software companies is obviously much better aligned for users of those software.
All right, let's bring it back to the audience. Any more questions? Sure.
I guess I'll kick it off and I think. Oh, the question. So the question was, what have been the biggest obstacles to the adoption of probabilistic programming ideas and software amongst users who are not necessarily researchers in the field or intimately familiar with the methods? So I'd say the first bit in terms of wider adoption amongst people who aren't kind of intimately familiar is just being reasonably familiar. So I think wider dissemination of the ideas has yet to happen. I think that's maybe, I can't tell whether it's just a marketing issue, like in terms of you just need to be, like we need to be more vocal about it and have better kind of simple blog posts and examples and Jupyter notebooks and things like that, or if it's a results problem where, or a task problem where neural nets did really well on image recognition, and so people that were working with images were like, wow, that looks good, I should use that. And that spurs development of blog posts and Jupyter notebooks and things like that. So I don't know exactly which one it is, but I think progress on both would be good. So having kind of nice results in kind of practical areas, as well as the kind of dissemination of knowledge bit. One thing I've noticed when people do start kind of thinking about it or looking at it, one of the biggest kind of interests is, hey, it'd be really nice to have good uncertainty estimates. And so that has been one of the drivers of some of the more, from people who aren't researchers, that's been driving some of the interest.
I think it's good to remember that probabilistic programming and probabilistic modeling, it's useful in cases so that it's not simple as t-test or black box as deep learning can be. It's useful when you know a lot about the phenomenon you want to model and you want to take this into account in your model, and then you are able to program that. But then it means that you also need to understand these modeling issues. You probably need to also understand a little bit at least the inference issues so that you understand what these diagnostics are warning that what is it working or not and so on. So one hurdle is that we need, of course, more training. That there's more people who understand these things, can use these methods to do better modeling.
Yeah, I was just going to follow up on some of the exact same issues. Yeah, I think that one of the big pitches for probabilistic programs is, oh, you can, it's so easy to encode the prior knowledge you have about your domain. But I think we need to think seriously about, who is the target audience that we want to be pitching these ideas to, who do have lots of prior knowledge about their domain. I think one of the reasons why the deep learning systems have been so wildly successful is people who know absolutely nothing about how to model language or how to model images can just throw this stuff at it and get some results, and I think that's really cool. So I think that the use cases and the target audiences are not necessarily the same at all, and I think that whether from a marketing perspective or a development perspective, it's important to think about that. And then also there's sort of this grand vision of, probabilistic programs, they'll totally separate modeling from inference, and the language developer will worry about the inference engine, and the language user will worry about writing the model, and they won't have to, the language user won't have to be an inference expert, and it'll all be beautiful. But in practice, to debug these systems, to understand how they work, you do need to know a little bit about that. And so I think that rather than kind of plugging our ears and saying, we're just going to, we believe our own hype, that it's a perfect separation between these two things. I think it's important to think about either A, how do you educate more people about at least some of the basics of how to diagnose kind of inference-based systems, or really try to make these systems live up to that promise more, make their error messages and make debuggers for them that are more interpretable to someone who maybe knows how to write code and knows a little bit about probability, but not as much about things like message passing or Monte Carlo or variational inference. That may be kind of a tall order, but I think that's the right way to be thinking about things.
So I do think it's useful to relate back to what has been successful, and there has been these neural network-based software. And considering it in relation to probabilistic modeling, it's really that it is easy to build sort of these compositional layers and do sort of inference in the sense that you're learning sort of model parameters. And this is just done by gradient descent. And probabilistic modeling is a lot more difficult and therefore requires a little more background for people who are just jumping into the field. But I think this sort of background is certainly necessary in order to achieve more ambitious tasks. And we've sort of seen this even in the deep learning field where people are trying to come up with very complex deep generative models and efficient inference algorithms on them, whether it be variational autoencoders and generative adversarial networks. And if you look at the current deep learning frameworks that are used for supervised learning on very large data sets, they're not very designed for generative models or anything beyond supervised learning. And this is really where I think this can be useful for sort of, I guess, deep learning and probabilistic programming to merge.
Yeah, so that's actually something that we've been looking at. So the language that I work on, WebPeople, has sort of a neural networks subcomponent to it, which you can use to plug into variational approximations. And we're actually looking at getting some fairly tight bindings to Torch implemented so that you can do some of these things like these structured deep generative models and things like that much more nicely. Kind of express them as just functional programs rather than these giant collections of stateful objects that have to somehow talk to each other in the right way.
So we are coming close to the end of the panel, but I'd like to end off with one more question that's sort of, again, at a higher level. What opportunities or open problems do you see in the near and maybe if you're more interested in the far future for inferential software?
Well, so okay, one thing that's I'll say is maybe more of a far future direction for
Keep it within 20 years.
Yeah, hopefully. Is so we have a lot of these languages now where you can write a model and you can flexibly switch what inference algorithm you want to try on it. So you write down your model and say, well, let me try MCMC, let me try SMC, let me try variational inference, mean field, or maybe I write kind of more interesting variational approximation. And I think a really big open question is in trying to more automate or semi-automate, just choosing what the right inference algorithm is, so that your less expert users don't have to spend a lot of time debugging this for themselves. That's kind of a sort of more longer-term mission. It's something that we've been interested in for a while, and I think if people could tackle that, it would really help adoption of this kind of software.
Just quickly, I think a really exciting short-term thing would be something in the diagnostics and posterior predictive checks type thing. I just want to reiterate that's an extremely important thing for any application, and I think the current set of tools is woefully, lacking. So there's an opportunity there.
I think given the current collection of really heterogeneous sort of approximate inference techniques, I think there's a lot of useful insights to glean just from trying to merge these ideas and see what's sort of like common among them. And we haven't really done that in so much, but it's very clear that there are approaches to do variational inference using some form of Markov transition kernel, or alternatively leveraging MCMC for variational inference. And I think it's sort of interesting to do this, and this sort of enables, I guess, a trade-off curve where in practice, there's always trade-offs that we make, both statistically and sort of computationally in our posterior inference. And we don't really have a way to sort of choose a point among this curve and define what is the best inference algorithm for that purpose. And in merging these sort of ideas, I think we can get better at that.
One thing is currently people are recoding a lot of things, so there's not enough libraries which would implement the kind of the basic things, and which libraries would be easy to use from different languages and so on. We can think of the like Plus and LAPAC libraries. You don't need to implement those things, and they've been really carefully optimized, numerical accuracy, stability, and so on. And I hope in the future we would have this kind of libraries, so that you don't need to worry that when, like, for some density you with some parameter values, you suddenly get infinite or not a number out of there, and then everything fails, and you need to re-implement that density function then you're on, and so on. Modularity, sharing code is really important in the future.
This is something that's much more speculative, but I'm particularly interested in or kind of to see research applying sort of some of this meta learning and learning to learn, some of these ideas to inference, particularly when it comes to kind of when you have discrete random variables in your probabilistic model. So it would be, yeah, I'm particularly curious to see how these kind of the learning community and deep learning, some of these meta learning concepts, how they might merge with both, sort of relaxations of exact inference and variational inference, just because it is sort of inference as optimization. Some of the stuff are, kind of immediately applies, but on some of the other inference algorithms, I'm curious to see if we might actually be able to improve them, or in some way by applying kind of some learning algorithms.
So unfortunately, I believe that is all the time we have. Let's thank the panelists. I believe there's a coffee break right now.